Hey, this is our project. We're going to present benchmarking 10 deep learning models for fine-grained video action recognition on something something V2. This is our final project by all of us.
Yeah, so our data set is something V2. It came from Qualcomm around 2018 and quickly became one of the standard benchmarks for fine-grained action recognition. The split is 168,000 training clips, 24,000 validation clips, and 27,000 validation test clips. The total ends up being around 220,000, and each clip is 2 to 6 seconds long, recorded at 24p, 240p. Each clip is a short video of a hand doing something to an object on a table, picking it up, putting it down, tearing it, plugging it in. Nothing crazy or nothing fancy. There are 174 action classes, and every label is a templated sentence with placeholders. The hard part about this is that the labels are direction sensitive. So, for example, pushing something from left to right is a different class than pushing something from right to left. Uh, that means you can't actually horizontally flip clips for augmentation, which is a common augmentation tool used in training image and video models. A lot of the class pairs also share the same arm motion and only differ in the physical outcome, for example, tearing a little versus tearing in half. Pretending to twist versus actually twisting, plugging in versus actually plugging out. These are different classes that look almost identical for most of the clip. That's what makes something something V2 a big stress test on most models that aren't trained to have temporal reasoning like this. So we focused on 10 architectures and one benchmark. Our central question to ask when this project was which model family actually wins on something something V2 when you give them all the same data, the same splits, and the same evaluation script. The way we approached answering this was by using four CNN-based TSM, a 2D ResNet with temporal shift, R2 plus 1D, a factorized 3D convolutional network that separates 2D plus like a 1D time operation into it, slow fast, which is another model that we use that has like two inputs from time. Then we had our transformer models. Time is transformer, which alternates spatial and temporal attention to keep memory tractable. Video MAE, which is a pre-trained vision model or vision transformer with masked autoencoder reconstruction. And then four other models that don't fit into the CNN or transformer category correctly. Um, for example, Video Mamba uses a state space model instead of attention, which gives linear time mixing. SDGNN, which runs convolutions over media pipe body points, but no RGB detection at all. And then PredRNN is actually our only world model in the current entry that uses a recurrent next generation frame predictor for classification. Qwen 3.5 4B, which is a vision language model that's unified. It's not two separate inputs into the header. And then we also used VJEPA 2, the small version, from Meta as our state-of-the-art reference. We specifically did not train this. We just ran its evaluation as basically a baseline for us to compare to. For our evaluation metrics, every model in the table is scored on the same 25,000 clip validation set. We use top one accuracy, which is a fraction of clips where the model's argmax matches the ground truth label. We use top five, which is a fraction where the right label sits anywhere in the model's top five predictions. A weighted F1, which is the support weighted average per class of the F1 score. We use that instead of mean accuracy because our validation split isn't perfectly class balanced. This helps normalize it. Per class, F1 is the harmonic mean of precision and recall. And then every model produced a 174 by 174 confusion matrix. At least that was the goal, which we will show, is shown in our actual report. And then one big caveat to flaw that we didn't think about when we were first setting up this whole project was that Quen classifies generally, it outputs text, not that 174 by 174 dimensional probability. So there's no actually ranked distribution for the top five from that. So we actually marked as top five as undefined.
Some things that got in the way during training. The first one was incompatibilities between certain GPUs that we use on Vast AI and certain PyTorch build that caused crashes mid-training. There was data loader stalls with WebM files decoding with video MAE. Vast AI migration for Coin and Pred RNN to escape Windows data loader contention. Label ambiguity in SSV2 templates and labels for the dataset hidden by Qualcomm. That was just uh, implicit in the data and couldn't really fix that.
Yeah, so some things that we built that were common across all models is that we could train in batches of 8 or 16 frames per clip. It was the 224 by 224 spatial resolution. This ImageNet mean normalization for some of the model that was shared. There's no horizontal flips. Um, no, we used Atom, W, or SGD with cosine learning rates for basically all the learning rates and scheduling of them. Some weird model specific things was that for Quen, specifically the QLOR, we used an R value of 16 and an alpha of 32. This helped actually speed up the training protocol a little bit and not help to make be so fine-tuned. We only did on the K, Q, V, and O caches, just because of overhead in terms of our GPU capacity. For STGCN, we used a learning rate of zero point 0.1 and a step to get it 30 to 40 because it only supported the key point tracking and motion of it. Um, Video MAE, we had to use at a BF16 and a learning rate of 5e to negative fourth because of using a V100. Same thing for time as transformer. And then the video Mamba K400, which Kenneth will talk about more later. Um, the initialization and stuff like that was a little bit weird because of the two ways that information flows throughout it. So this is the headline result. This is basically every model we trained sorted by the top one accuracy on the validation set. VJEPA is at the top, with 64% as a reference. We didn't train it, we just loaded the frozen weights. Quen is next at 58.19%, which was a surprise. One epoch of QLoRa fine-tuning on a vision language model where only 0.12 of its parameters were trainable produced this great of a result. Um, this is 6 points below the frozen ceiling, with basically 100 of the trainable parameters, especially at a model this small, shows great effort in making maybe spatial understanding more viable. Video Mamba sits at 53.91%, which is even more striking because we only ran two epochs. The pre-bug fix version of the same architecture is at the bottom at 1.45. Kenneth handled fixing all of that, which was super dope. In the middle, you have R2 plus 1D at 46, slow fast at 36, and time is transformer at 34. These were the pre-trained CNNs and transformers, all initialized from the Kinetics 400. Last to a person more CNN plus con LSTM at 27%. Um, this did worse than we expected it to, specifically because of the hybrid architecture we put there for the spatial understanding. And then one was for video MAE at 17%. TSM actually had a really crazy overfit where we ended up having like a 90-point training accuracy number, but then like almost like 6% or something like that for TSM. It was really weird. So the pattern is clear though across the board. Pre-training helps in most cases, not per se the architecture. So then VJEPA stands for Video Joint Embedding Predictive Architecture. It's from Meta's self-supervised video model of 2024. The key idea is that it predicts masked video patches in future space rather than trying to reconstruct the pixels. So during pre-training, the model actually never renders textures or backgrounds. It just has to get the right features with its attention mechanism correct. It gives a much cleaner representation of downstream tasks. The backbone is a vision transformer. Um, and it's trained on Meta's video mix 2M dataset for 90,000 iterations. Our number of 64.51% is higher than, or sorry, is lower than what was anticipated. We evaluated this specifically for a little over an hour on a V100. And like I said, it lowered about 5 points below Meta's published 69.5%. But the gap isn't because of the model itself, it's because of the V100. We had to set it to FP16 instead of BF16, and that caused a lack of precision on the model's part. For the next model, it was a Quen 3.54B with QLoRa. Quen 3.54B was actually unexpected because it's a multimodal vision language model with about 3 billion trainable parameters. Um, we treated it as a video classifier, which is not exactly what it was designed for at all. We didn't fine tune all 3 billion parameters, obviously. Instead, we did a QLoRa, which quantizes low rank adaptation down, just like normal LoRa paper. Initially, I wanted to apply Thinking Machines LoRa blog post where you add it to every activated layer, but that would have taking too much time and effort, so I just did it for the KQV and output caches. Um, the adapters ended up being super tiny, where it's basically 0.12% of the actual model's trainable parameters. Its classification is generative, like I said. We fed in 8 frames at a time, plus the prompt, so we can unify the model's language understanding to its visual understanding. And then after that, it took 43 hours on a 5090, which is long, but worked pretty well. Um, and then for the compute constrained settings, like this is the practical takeaway that small adapters on a frozen VLM for one epoch beats a from scratch 18 million parameter dedicated video model for 15 epochs by more than 50 points. Um, this shows that these small models, there is a viability there for more world model generation, classification, maybe prediction for the future, if they're more aligned in that direction.
Thank you, Manish. So Video Mambo is a really interesting case because it's a state-space model. So with the way it works, it scans the video both forward and backwards in order to validate what it sees and get the most accurate results. So our first run on 10 epochs was using untrained weights, so just the base weights straight from the factory lab, and we got a only 1.4% rating essentially after 10 epochs. And after some analysis, we kind of concluded that it was because of the fact that the implementation we used on our specific torch was only unidirectional, so we're only scanning forward. So that was losing half of the model essentially, which is a major, major loss and does not accurately represent the video Mamba itself. So to kind of get a better baseline, we used the K400 pre-trained model from OpenGL Lab directly, and this had a much, much better results. So as you can see, it got a 53.91% score in just 2 epochs. And these epochs were a lot slower than the initial run, and that is because of the setup. So essentially, um, with the bidirectional Mamba, the Mamba inner FN is the fused CUDA kernel, and it's hard coded for unidirectional scan, so it won't accept those backward parameters cleanly. So the two options were to either hack the fused kernel to handle the bidirectional stuff and possibly risk silently producing wrong outputs, or is to fall on the selective function, which is the selective scan FN, which scans both layers twice, which is it's going to cost a lot more, but it is the correct output. So unfortunately, from our results, that was 3 to 4% slower per step versus the initial video Mamba testing. So that was something to handle. And the lesson to learn here was to run some smoke tests essentially and just check to see what our validation accuracy was after just a couple batches and as opposed to wasting a couple hours. But definitely after 15 epochs on the pre-trained model, this would very easily go to top 1% compared with JEPA and probably surpass it actually.
Now we have the R2 plus 1D, one of our CNN models. It got a top 1 accuracy of 46.36% and a top 5 accuracy of a 74.84%. It uses spatial temporal separable 3D convolutions, and we use the R2 plus 1D 18 pre-trained weights. We did 30 epochs on an RTX 5090. It took around 105 hours. And this model pretty surprised us, and it was a great sweet spot for cost versus accuracy because this was like a scratch model.
Yeah, and just to go over the slow fast and timesformer convolutional models, the slow fast performs slightly better than timesformer, even with the crash mid training. These were both run on 5090s for roughly 15 epochs. Slow fast was initialized with um, 8 frames for the slow path and 32 for the fast one. And the loss was steadily decreasing and then leveling out as it crashed. The top five accuracy was 69.34%. F1 was 0.5.
All right, next is the CNN plus Archon LSTM. This is a kind of combination of two different models. The architecture, just really briefly, is a per frame resonant 18. So it's an ImageNet 1K pre-trained. Spatial features are B times T, 5, 12, 7, and 7. But we actually reshaped that with the Conv LSTM to B, 256, and 77. So this architecture is really cool because it allows the CNN essentially to operate more efficiently in the action world model space that we're working in. So the headline numbers is a 27.1% or 0.01% top 1K. And that is pretty surprising actually. Did pretty well compared to the other models. especially after 15 epochs, which is about 4 times better than the TSM with a similar training budget. So it was surprising to see this model perform so well as a CNN. A quick look at the data. At Epoch 1, our validation was only 5.4%, and then around Epoch 14, that's when we had our best, which was 27%. So things were actually getting pretty better, but around Epoch 15, we decreased all the way down a tiny bit from 27 to just 26.9, so just a 1% plateau essentially. The best class here was the turning camera from left to right while filming something, and that was an 83% accuracy. And our lowest of the top five was 72%, which is turning the camera downwards while filming something. So compared to Video Mamba for 15 epochs, they took both about the same time. So the two epochs of Video Mamba took about 8 hours, and so did the 15 epochs of CNN. So it was cool just to see how 15 hours spent on two different models, two different architectures can really change the difference between our validation top 1% score.
So this is our video May model. Um, so it reached 16.92% top one accuracy after finishing 11 out of 15 epochs. Um, we used the VTB16 backbone with K400 self-supervised pre-training and full fine-tuning. So this was one of our stronger transformer-based baselines.
And here's our temporal shift model, which is another CNN model. We used a ResNet 50 pre-trained weights with the temporal shift in each bottleneck. We did 30 epochs. The training accuracy reached 96%, but the validation accuracy was stuck around 6%. This shows like a massive train and a validation gap, which is just a classic or overfitting problem. And the temporal shift we decided was not enough for the something something V2 dataset.
Sorry, I was on mute. Thank you. So Predator N was our only world model entry. The architecture came from 2017, originally designed for next frame video prediction, not classification, kind of similar to how Quen was. The core unit is a spatial temporal LSTM. Which in this case is an LSTM cell that has two memory pathways instead of one, the standard temporal memory pathway in this case, and then a spatial memory pathway. And it zigzagged, the layers zigzagged throughout each other. We stacked four of those cells on top of each other, plus a CNN encoder to downsample to the 224 by 224 frames. It resulted essentially in a 4.67 top one, and then roughly 70% of the classes got 0% accuracy. The model only learned motion heavy classes where there was a clear global direction signal, and then a camera direction class. Surface placement classes it really struggled on, and then everything else it kind of just failed on. This was by far the most confused model that we used. The lessons that Pred RNN learned global motion direction, but it didn't learn things like gravity, weight, lack of grip, if maybe if something fell in one of the videos. World models should be able to predict what visually comes next, but that doesn't technically mean a world model like this translates to recognizing what's happening physically. And then that's kind of where like real limitations start to crop up. So for STGCN, we achieved a 3.94% accuracy on that. The weird thing about STGCN is that it's also paired internally with MediaPipe. Um, that means it only tracks skeletons, not actual image and object recognition. Um, the actual MediaPipe pose detection rate itself through all the videos was 55%, and it only ever really worked on the something something V2 frames that showed hands, not bodies. So whatever media pipe model that they're using specifically is the hand mark one, not the land pose one. That's probably just due to limitations in terms of how quickly this can run in training and putting it all together. It is very small at only 3.1 million parameters, and for it to achieve almost what Predator and N did is actually super cool. Essentially, both are fundamentally limited on fine-grained hand-object interactions. These are our per-class winners and losers. Overall, we see that the camera motion classes are easy across all models, but the pretending and the physical state classes are hard for everybody. Um, Again, like Quen got pouring something and something at almost full accuracy, right? But it really failed at tearing something into two pieces, and then there's like subclasses within that also. Overall, it was a cool experience to have, but it really struggled with the still temporal causal actions that just happen naturally in our world that world models should be getting pushed to understand.
And these are our four lessons that we learned. First, that pre-training the models dominated in the something something V2 dataset. And for the video Mamba, we realized there's two modes. There's a accuracy mode and a speed mode, and the accuracy mode was better, even though it did take like 4 times as long to train. For the SCGCN, the skeleton only vision was limited. It was like kind of too rigid. And the VLMs were competitive. The Quen's parameters, only 0.12% of them were trainable, and it still had a 58.19% top one accuracy.
And so for our conclusions and future work, the first thing is rerunning VJEPA on an A100 GPU with native BF16 encoding to recover that published 69.5%. That will be really helpful just to see the baseline and to see maybe to push this model a little bit to see what it can really get on this specific data set in the real world. The next thing is a full 15 epoch video Mamba run with a fused Mamba inner FN. That way it can run both directions, scanning both for accuracy, taking slower, but just to be a fair evaluation, and we should suspect around a 58 to 62% in the top 1%, which is great. Next thing is a multi-model fusion. So as Ayan just mentioned, the SDGCN skeleton was kind of the weakness because of the fact that it was only getting the hand, and it can only see kind of not in RGB. So mixing that with a R2 plus 1 dimension RGB, that'll make it a much stronger model in the long run. And longer Quen training. So 3 more epochs would probably push it past VJAPA, which would be like really cool results to see this Quen model doing so well in this sort of case. And the final thing is curriculum on the pretending and physical state classes that defeat everybody. We see that there's a couple classes that really took a hit at every single model. And so some more fine tuning on the specific actions and those specific labels would probably produce better results for the entire experiment. Thank you so much. This has been our presentation.